Hello, welcome to another in this series of videos on the science of accident reconstruction and how you perform the dynamics in an accident reconstruction scenario. What we will do here is we'll actually look at how we determine the initial speed of a vehicle from skid marks left by that vehicle. In a previous video entitled Skid to Stop, methodology was presented where you start with an initial speed which is known and you determine how far the car will slide to a stop. That's actually not how you see the problem presents itself to the analyst. What normally happens is you know the end state of the vehicle, and you use that end state and then actually work backwards to find out what the initial speed or speeds, if there's more than one vehicle, are. These initial speeds are used, they're needed to assess the blame in the accident. So what we'll do here is we'll actually see how to do this. We'll start with the final state and work our way backwards to the initial state. We're going to add a little complication to this problem. In the previous slide, we actually had the vehicle we had an initial known velocity, and we determined how far the car would slide to a stop. What we're going to do here is we're actually going to let the final velocity not be 0. So we will have a known final velocity. We'll have a skid length, and we will determine what the initial velocity was. One can often estimate this final velocity with some degree of precision from various ways to do it. We'll get into those in later videos. This slide here actually illustrates how we're going to solve our problem, what physical principle is going to be applied. And we're going to use work energy again, as we did in the previous video, skid to stop. Basically what happens is we start out here with a initial energy state. We take energy out of the system through the friction of braking, and we wind up with a end kinetic energy state where the velocity is less than the initial velocity. So Vf will be less than Vi because the energy has been removed from the system. To express this in words, the end kinetic energy state is the beginning state minus the energy lost during the skid. And this equation that is shown here illustrates, or actually expresses, that thought, the application of that principle mathematically. In that equation, mass appears in every term in the equation, so it can be divided out. And what this means is that mass actually plays no role here. Actually, it scales the problem. We have more kinetic energy with a heavier vehicle, but then we have more energy taken out of the system by braking. But overall, we can neglect the mass because it's in every term and it can be divided out. What is unknown here is the initial velocity, so we can get this equation and solve it for the initial speed, and that's what's shown in this equation here at the bottom of the second equation. Let's use this to test our analysis out with a problem that we already have answers for. Let's let the final velocity be 0. That should still work. We'll use the friction coefficient, or the drag coefficient as it's called in the world of accident reconstruction, of 0.7. and we'll have a skid distance of 172 feet. We worked that out previously in the skid to stop video, that the initial speed for this case would be 60 miles an hour. So let's see if we get 60 miles an hour working backwards. And actually, if we do that, we plug our numbers in. I've shown the units here, etc., and how it's calculated. We wind up with 60 miles an hour. You have to be careful with the conversion from miles per hour to feet per second. That's a common, typical mistake to make, but it's shown how to do it here. One thing that I do when I'm checking, actually, is I know that the number for miles per hour is always less than the number for feet per second. For instance, 60 miles per hour is about 88 feet per second, so that's a good check. Your feet per second should always be more than your miles per hour for a given speed. I've already said this. This confirms our reasoning, that our reasoning is consistent with the previous result, and this is how the situation would be presented, the end state, actually, to the accident reconstructionist. Now let's work a second problem where we have a non-zero end speed. So the car has not stopped. And let's just use it as an example. We somehow or other have figured out that the car at the end of its skid is traveling at 30 miles per hour and everything else is the same. Now, an interesting question to pose to yourself is this just going to shift the initial velocity up by 30 miles per hour? So instead of starting at 60, we start with 90 and go to 30 with the skid length, friction factor, etc. Is that what's going to happen? So we'll pose that and we'll take a look. We solved this, but this time we have not eliminated our final velocity. We've put it in as 30 miles per hour. Notice that it's converted to feet per second. And then we also have in here the energy lost during the skid in the formula that we previously worked out. And voila. We wind up with a speed of 67.1 miles per hour. So no, starting at an end speed of 30 miles per hour does not mean that we started with an initial speed of 90 miles per hour. Because of the square root relationship and the square relationship under the square root, this relationship is not linear. One thing that we can say, though, if you look at the term that encompasses the energy removed from the system, it's exactly the same term in this case as it was in the previous case. So the amount of energy that is extracted from the system in a 172-foot skid with a drag factor of 0.7 is the same regardless of what end speed you start with. And that's the end of this presentation. Thanks for watching. Look for more videos on accident reconstruction appearing on this website.